Adjacency matrices combine two of the important topics in the course, graph theory and matrices. An adjacency matrix is a matrix that describes a graph by holding all of its information, but in matrix form. Here's a graph. It has 6 nodes, it has 1, 2, 3, 4, 5, 6, 7 edges, and I could describe this using a matrix. The first thing to note about an adjacency matrix is that it is always square and has the size that's the number of nodes in our graph. So the adjacency matrix for this graph with 6 nodes would be 6 by 6 square. And I like to always label it using the node names. So in this case, numbers 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So each row or column represents the edges that connect to that node. So for example, let's look at node 1. Node 1 has connections to node 2 and node 5. It has one edge to node 2 and one edge to node 5. So I can put a 1 in that entry from 1 to 2, and in that entry from 1 to 5. Every other entry will be a 0. There are no nodes connecting 1 to 1, 1 to 3, 1 to 4, or 1 to 6. Let's do the same thing for node 2. If I look at node 2, I see it connects to node 1, node 3, and node 5, and none of the others. Node 3 connects to 2 and 4, and none of the others. Node 4 connects to 3, 5, and 6. Node 5 connects to 1, to 2, and to 4. And finally, node 6 only connects there to node 4. Let's look at this adjacency matrix and take note of a few important features. The first important feature to note is the values of all of these entries. Every entry in this matrix is either a 0 or a 1. That's because our graph was simple, meaning that there will never be more than one edge connecting two nodes in a simple graph, and there aren't any loops, an edge connecting itself. Loops would be found here on the diagonal, 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, or 6 to 6. We don't have any loops, so that diagonal is all 0. We don't have any parallel edges, so every other entry is either 0 for 0 edges or 1 for 1 edge. Another important thing to note is that this matrix is symmetric. In other words, every row is the same as its column. Row 1 represents what happens to node 1, just like column 1 does. They're exactly the same. And if I add up the entries in any row or same column, I'll get the degree for that node. So again, if we look at that first row, I see that node 1 has degree 1 plus 1, 2. Node 2 has degree 3, 3, 2, 4 has degree 3, 5 has degree 3, and node 6 has degree 1. So the row or column sum in our adjacency matrix gives us the degrees for each of those nodes. What if our graph is not simple? Here we have a similar graph, but with one parallel edge between 3 and 4, and a loop on 1. Again, our matrix will still be a square with the number of rows and columns equal to the number of nodes that our matrix has, so we can label it the same way for the rows and the same way for the columns. And again, let's go through and add the entries based on each node. So node 1, I can see that node 1 actually does have an edge that connects to itself. That would be a loop right here, one loop. Then it connects to 2 and it connects to 5. Node 2 goes to 1, 3, and 5, same as before. Node 3 goes to 2. This time it has 2 edges joining to 4. So that 2 represents our parallel edges. Node 4 joins twice to node 3, once to 5 and once to 6. Node 5 joins to 1, 2, and 4. and node 6 just goes to 4. If we want to talk about the differences between this adjacency matrix and the last one, we can see a few of them right off the bat. The first difference I note is that if I look at the diagonal here, they aren't all zeros. I've got this 1 that represents that loop that was there. The second difference is that some of the entries are not 0 or 1. I have some entries that are 2s. Those represent the parallel edges. So if we have a graph that's not simple, like the one drawn here, then we'll see entries on the diagonal, and we may see entries that are larger than 1. Still, every row and column are the same. So I should still get the degree of each node if I sum up each row or column. Let's start from the bottom this time. Degree of 6 is 1, good. Degree of 5 is 3. Degree of 4 is 1, 2, 3, 4, because I count both of those edges connecting to 3. Degree of 3 is 2 plus 1, 3. Degree of 2 is 3. And according to my row sum here, the degree of node 1 should be 1 plus 1 plus 1 makes 3. But it's actually not. That's one edge, that's one edge. A loop actually contributes twice to the degree of a node because it touches it twice. So if I'm looking at the adjacency matrix and I see an entry on the diagonal, I'm actually supposed to double just that entry when I add up my degrees. So that entry is a 1, but it counts for 2 in my degree. So 2, 3, 4. The degree of node 1 should be 4. So if we're looking at an adjacency matrix for a non-simple graph, we need to be careful when we add up the row sums for degrees and watch out for loops. The last type of adjacency matrix we'll look at is for digraphs. These, again, start out in a very similar fashion. So this one would be also 6 by 6, one row for each of our nodes, and one column for each of our nodes. Now, however, our rows and columns won't be the same necessarily. Think of rows as describing what node we're coming from, and columns as what node we're going to. So if I look at node 1, if I try to go from 1 to anywhere else, I can't. Node 1 goes from 1 to nowhere. How about 2? If I look at 2, I see that I can get from 2 to 1 here. So I can get from 2 to 1, but that's it. Where can I get from node 3? I can get to 2 or 4. From node 4, I can only get to node 5. From node 5, I can get to 1 or to 2. From node 6, I can get to node 4. Let's look at one of the rows and columns. Let's look at row 1 and column 1. I see that row 1 is all zeros. Column 1 has 2 1s in it. They're not the same anymore. And this matrix is not going to be symmetric. It could be if we had an edge going back for everyone going forth, but in a digraph it doesn't have to be. We could still have loops, we could still have parallel edges, but now we have 2 different degrees for each node. We have a from degree and a to degree. So for node 1, the degree from node 1 is 0. The degree to node 1 is 2. 2 edges going into it, 0 edges going away from it. That's your little summary on adjacency matrices. I'll see you in the next video.